1 times 4, 1 times 4 is a square. 1 times 3 is a triangle. 1 times how much makes a circle? 1 times 4, perimeter. So 4 divided by 2 times poi. Who's this? So this is representative of the radius, while the one above is representative of a full length of a square. So what to do now? Pythagoras. Let's say the radius right here is the height of a right triangle, and let's say that number 1 right here would need to be divided by 2 in order to have maybe the left side or the right side, preferably the right side of a right triangle. Okay, so we're going to calculate that. So that would be 1 divided by 2 squared plus that squared equals that. And badao, what do you know? What does that look like? Multiplied by 2, it looks like a golden ratio. What do you know? It looks like a golden ratio. Okay. So let's do this. We're going to take the equation for the golden ratio, which is 1 plus the square root of 5 divided by 2, and badao, that is the golden ratio. The reason why that is not the golden ratio is because it does not have the same properties as the golden ratio. For example, if you do 1 divided by that one, it gives us 0.617, as opposed to the golden ratio, and it's the reason why it's known as the golden ratio. 1 divided by the golden ratio gives you the golden ratio minus 1, which is rather extraordinary. If we input like precisions just to see exactly what we're talking about, right there, and that one right here, that's a golden ratio, and that one stems from that pi. So it's easy to know again what that one is. If you multiply by 2, that looks a whole lot like the square root of a golden ratio. And if I were to take the golden ratio and do its square root, that's what we get. So if I were to take that number divided by 2, And then I would do 4 divided by 2 times that one. It would give us the real pi, which is 3.14460551103. Okay. The reason why this one is called the real pi, mathematically speaking, it's not as simple as anybody would think. There was this guy, I think he died, I'm not too sure. I was looking for his name recently, and it seemed as if he recently died. So, I mean, his name was Samuel Laboy, and the guy was an engineer, and he went to Egypt, and while in Egypt, he did some calculations on the Pyramid of Giza, and I mean, the greater majority of people just did not take this into consideration, really. I mean, if ever you're going to try to figure out what pi is all about, where pi came from, you have one thing that's called alchemy, and in alchemy, the word alchemy itself comes from alchemet, alchem, and so in there they explain, like, in details, in length, what is squaring the circle, and so if you want to square the circle, you need to have the same parameter as the circumference of a circle. Like the circumference of a circle needs to be exactly the same as the perimeter of a square, and so the base parameter of a pyramid is a square. What do you know? And so if ever we would consider the height of a right triangle in Kepler's triangle, and basically what this means is that a base parameter divided by the radius, which is the height of the pyramid, gives you pi. And so you can try it. Let me see. It's base parameter divided by 2 times the radius. Yeah. So in this way, base parameter divided by 2 times the radius, it will give you pi. Try it. But it works only with a perfect pyramid. And the equation, and the way it is done, is like this. Check this out. We try that. 4 squared divided by pi. Okay, it gives us that. Okay. Squared minus pi squared. And normally you would get the exact first number at the very beginning, which would be, well, squared at that point. 16. 4 squared, basically 16. Bow. Oh, it's not giving us that. Okay. Let's try with the other one then. And good for all y'all. Save that. So here's what this looks like. Yeah. I redo the same equation, exactly the same. Squared minus the same pi squared. And lo and behold, with a precision of 12, boom, 16. If I do multiplied by 2, 16 divided, so 32 divided by, let's say 2 pi, 32 divided by 2 pi gives us that here. And so if I do pi multiplied by this, normally it should give us 16. Yeah, you know? But when we do, let's say for example, that squared minus pi squared in order to find the radius, you see it doesn't give us 16. You know? It gives us something else. This property does not occur with the true value of pi. You know, with the true value of pi, if let's say for example I do 16 divided by pi, it would give us this, right? Or if and then after doing that squared minus pi squared, and I say pi squared, but now, what do you know? What do you know? I mean, this is like the only one that gives us something like this, and I have to show it like in the proper way so that you can understand it clearly. And it's like this. It is 4 multiplied by the square root of phi squared plus 4 divided by the square root of phi squared, giving us, snap, I made plus instead of doing minus. But it's okay. That number is cyclical. You don't believe me, right? Okay, so let's see. 35 minus 19. If I do that, okay, that's 16. So let's go back. Minus 16, bow, divided by 2, bow, and then cyclical, as I told you. That pi is magic all, but it does not prove what I wanted to prove because I made a mistake a few moments ago. But what I'm trying to show is this. So I'm just gonna ease your pain again with the eyes when it comes to the goal, that here. Okay, so basically it's 4 times that squared minus 4 divided by that squared, and then gives us 16, and then gives us 4, you know. And that works only when 4 divided by that is equal pi, that thing. That is perfection. And not only that, there's a concealed pi within that pi. So you can find another pi which looks almost the same as the transcendental pi. Okay? And so the way to get to that is that you take that one here, and then you divide it by 4, and you recognize this in trigonometry. In trigonometry, okay, y'all, that's pi over 4, right? Pi over 4. Okay, so you take that pi over 4, and then you square it, so that gives you 1 over the golden ratio. And then after that you do the 1 over the golden ratio, and then after that you square the golden ratio, and then you divide it by 5 over 6, which gives you another pi, which of course I do not know what that other pi is all about. But one thing is for sure is that when you divide that other pi by 6, it gives us something that looks so much like the qubit. And when you do the square root of that so-called qubit, it's exactly the same. It's exactly the same. It's exactly the same. Minus maybe 2 decimals. No, not 2 decimals, but 0.2, you know what. I don't know. I'm not so good in mathematics. You tell me. Still, isn't it impressive? And so, that's one thing that I found pretty much impressive about that number pi, that pi here, which reveals another pi right here, which looks so much like this pi right here. But that pi does not do that same property as that pi right there, in the sense that its qubit is exactly the same as that is right here, you know? So you could try with 22 divided by 7 divided by 6, and then you try. It doesn't work. And I mean, I try to get with even that one, you know, divided by 6 and then square root. It doesn't give out like what would be expected of it, you know. Although I'm looking at something and I wonder. Nope, nothing. Okay, it's really just that other one again that has like I guess it's a perfect qubit. It has to be. And to get to that one, you need to do 3 divided by 5 multiplied by 3 plus the square root of 5. And the square root of 5, I don't know why, okay, but it's very special. And that's that square root, okay, that reveals the golden ratio in all its splendor. So number 5, okay, is very important, as well as number 7, number 3, and practically all the 9 numbers, pretty much sacred. And yeah, so, and I know, okay, this one is the correct one, because when I do that divided, is it divided or multiplied? Well, it's multiplied. Yeah, multiplied by 5 over 6, it gives us the square of the golden ratio, if I'm not mistaken. Bow. Yup. Like I said, that one again is pretty much mysterious, as I said before. It divided by 6, that's pi over 6, you know, and it gives us that. But I mean, that part is a little bit tricky, because if you do that multiplied by 180, and then if ever I were to divide it by that pi instead of the other pi, it will not give you 30 degrees. It will not, because in order for it to be 30 degrees again, it needs to be the exact pi on both sides. So it works again if, let's say, for example, I take the other pi right there, the first one, and of course it's going to give us like the 30 degrees, no doubt. But the same goes if ever I take that pi, you know, if I take that pi divided by 6 multiplied by 180 and then divided by pi, what do you know, it gives us 30 as well. So that one is tricky. You cannot, it's not an actual proof. The real actual proof of it would be with the squaring of the circle itself, a parameter to circumference, you know, the one again where it shows that if you do 16 divided by 4 equals 4, and if you do 16 divided by no, I guess again, yeah, I wouldn't be able to get to do it like that. It's well, a good way to visualize this again would be to do the formula like that Samuel LeBoy has been doing. And that formula like it was pretty much good. And so, and I'm gonna multiply this by 10 so that in this way it can be shown properly, you know, multiplied by 10. I multiply by 10. Wait. What I multiply by 10? Wait up. Okay. So, let's see. I take that. Take the grid. And multiply by 10. Right there. No, I'm not gonna do 10. I'm gonna do 4. 4 okay, is always better. 40 maybe. No, I'm gonna do the square, the golden ratio. Square root of the golden ratio. Okay, square root of the golden ratio. So I'm just gonna calculate this real quick. Square root of the golden ratio. Square curse. Now you see, that's what it's shown. Like, that's wrong. That's not supposed to be that. And you'll know it's wrong because once I do the formula and the square appears and reveals the truth, the circle doesn't mean anything anymore. You know, it's like it shows like the true hubris of some scientists who they themselves believe that, oh yo, we know everything. Nah, you don't know everything. In order for you to know something, okay, yo, you need to study and study and study and study. And the things that you need to study, okay, you ain't gonna find at the university or at school. Yeah, it's all nature. It's all nature. It's all in nature. You know? That's how it is. That's how it has always been. That's how it should be. So let me go back on that. Let me go back on that. Let me go back on that. Okay, so I said like that I was going to change the radius to the square root of the golden ratio. So first I'm going to do the equation of the golden ratio, and it's rather difficult to do that equation on geometry pad, but I mean geometry pad has been the one application I've been using in order to do this, and I'm so used to it, so I'm not going to change for anything else. So 1 plus the square root of 5 equals that, and divided by 2 equals that. Right? Now, this one I guess is way better it's way better if I do it with that one, because if I do it with the golden ratio will reveal pi within the square itself, which is rather extraordinary. And on one side of the square is going to show pi, and it's really just going to show the pi that I mentioned previously, the only one which is rather connected to that geometry, you know. And I don't know, maybe there's another one that's connected to the other pi that was connected to that pi, which is connected to the golden ratio, which is connected. That's when it's connected, you have to tell yourself, which more is more important, one which is transcendental and comes out of nowhere, or one that has like a purpose and is balanced with everything else. You know what I'm saying? It's logic, right? But then anyways, never question the logic of a planet who's not logical. Who said that? Okay, so yeah. Let me go back on that. You see here, it says the circumference is a 10 dot close to 17, you know. But let's do the formula. The formula that Samuel LeBoy, engineer, did was creating a Kepler's right triangle using like like geometrical forms, you know. And basically, the claim that he gave was that there's no need for you to have like any numbers surrounded around this, because at the end of the day, you'll always end up with the same number pi. Always. Like, I've tried it numerous times. It's rather scary, I would say. Just one a sec. Okay, so after that, take another circle. You've seen the videos. I've done the videos before. I've done several of them videos, but I just uncovered that point connected to that point, it's exactly 30 degrees, like exactly 30 degrees, like no cap. It's exactly for 30 degrees, so it connects. It's just that for the construction that we're doing, the circle is smaller than the square, and it's gonna show. But mind you that everything that we're doing right now, they're all connected. So this means like that you know, this circle is connected, that circle is connected, that circle, and then I take the connection to one circle, the next circle, you know. So if I take a line here and I connect that here to that here, let's just say that I have a compass right here, and I put the tip of the compass right there, and I do a circle, and I do it from here, you know. I mean, you're not losing anything because they're all part of the same. It's like building a flower of life. It's like building a flower of life, as a matter of fact, you know. I take this off, I can take this off, and I can take this off. I don't need that. Now I have what I want, and I am going to do the triangle. Not the triangle yet. No, I'm not going to do the triangle yet. Yes, it's the triangle. What am I talking about? I am going to do the triangle. Okay, so I do the triangle right there. Wow. Then just erase that one right here. I won't need that. And I just I'll just do a green one like that. Green triangle. Okay. So I can tell you right now that the height, which is the radius of this circle, is the golden ratio. And